Hey everyone. In this video, we're going to be taking a look at transformers and not the robots in disguise kind of transformers, but the kind of transformers that can switch our current from a high voltage to a low voltage or vice versa. So if you remember back when we studied circuits, and we looked at the power that can be transported through circuits, and we studied how that if you have a very high current, you tend to lose a lot of power as that current is transported from one place to another. But if we can have, instead of a high current, if we can use a high voltage, with a high voltage and a low current, there's actually very little power loss. Um, Whereas with a high current and a low voltage, there's a lot. So in order to switch back and forth between these two situations, we use transformers. So just as an example of how power gets to our homes here. So we have a power plant. Okay, a power plant can produce electricity at around 12 kilovolts. Okay, that then comes through the wires in this direction and down into what we call a step-up transformer. Now, a step-up transformer, think the word up, increases the voltage. So it changes the voltage to 400 kilovolts. Now, you may have seen these wires around if you're driving anywhere, but these very tall towers, these are high voltage transmission lines. Okay, so they carry very, very high voltages. Then, when the current is needed, so when you get close into a town, you may have seen these around, so something like this. This is called a substation. Okay, and the substation takes these very high voltage lines and drops it down through another transformer, this time a step-down transformer, and converts it into a lower voltage down to around 10 to 13 kilovolts. Okay, this voltage then travels through our regular lines, and before it enters our house, we don't really want a 13,000 kilovolt voltage entering our home. We use about 240, or depending where you are in the world, 120, 240, somewhere in that range. We have on our telephone poles another step-down transformer to drop the voltage back down. And these look like this. So if you're in a community right now and you look outside at a couple of poles outside your house, you'll probably see a few of these around. Okay, so these drop the voltage to a lower voltage that's usable by our households. And again, the reason for this is we don't want that power loss. So during long transport periods, such as these large high voltage lines, we need to keep the voltage high to not lose a lot of power. Once we get really close to the house and we're only traveling a short distance, we can have a really low voltage and increase the current. Now let's see how we do that using a transformer. So a transformer, first and foremost, increases or decreases the voltage while keeping the power the same. Okay, and it consists of two coils of wire called the primary and secondary coils. So a simple schematic of a transformer looks like this. What happens is we have a current coming through this coil. Okay, it goes around the coil and exits out this side. As we know, when you have a wire carrying a current and it's coiled like this, we're creating a solenoid. Okay, and it's wrapped around what we call a core. So this piece in the middle would be, and this core would be made of some magnetic material like iron. Now what happens is it generates a magnetic field. We could use our right-hand rule here if you wanted to figure out the direction of the magnetic field, but it will be going in this direction as I currently draw it. So the magnetic field goes around, okay, through this iron core. Now what happens when the magnetic field, or the B field as it's often referred to, travels around the core, here it passes through another solenoid. Now there's no current inputting into this solenoid, but we know through electromagnetic induction as this magnetic field passes through the secondary solenoid, it's going to generate some electricity. Okay, and once again, you can use your right-hand rule to determine the direction of the current in this secondary solenoid. So if you remember from the previous one, in this situation with electromagnetic induction, it requires a changing magnetic field in order to actually generate that electricity coming in and out of this secondary coil. So this is where you may have heard of AC, DC, and not the band, but what AC stands for is alternating current, and DC stands for direct current. Okay, so an alternating current is a current that flips back and forth. So it would very rapidly change from going in this direction to flipping the current to the opposite direction. And what this does is it quickly flips the magnetic field. So you get a constantly changing magnetic field that's going in and out of the secondary coil, which makes a constant voltage being produced. Or we get an average voltage through the switching of the current. Okay, so when a current flows in the primary coil, we know that a magnetic field is going to be created around that coil. Okay, so we can, let me just switch colors here. We can calculate this, okay, because we know from a previous lesson that the voltage in the voltage is equal to the number of turns in your coil times the magnetic flux over the change in time, where P in this case is standing for the primary coil. So N would be the number of turns in the primary coil. Okay, so we can calculate the voltage that is going through a primary coil and figure out the magnetic field that's being created. We can do the same thing with the secondary coil. So the voltage in the secondary is equal to the number of turns in the secondary times the flux over the change in time. Now by taking these two equations, I'm going to just rearrange each one a little bit and move the number of turns to the other side. So this would be Vp over Np is equal to the flux over the change in time. Vs over Ns is equal to the flux over the change in time. So we know that the flux, it's all part of the same transformer. So this piece of the equation in both instances is going to remain the same. Okay, which means that we can equate these two things. The voltage primary over the number of turns in the primary is equal to the secondary voltage over the number of turns in the secondary. Okay, and we can combine these two equations to get this one, or you might see a different rearranged form of it somewhere, but essentially this. So the primary voltage over the number of turns equals the secondary voltage over the number of turns. If we have a step-up transformer, so one that's increasing in voltage, then the secondary coil is going to have more turns than the primary. Okay, and if we have a step-down transformer, then the secondary coil is going to have less turns than the primary. So think more, if it's going to more turns, that's an increase in voltage. If it's going to less turns, that's a decrease in voltage. Okay, so another thing is that the power, and we can't just generate power out of nowhere. Of course, there'll always be a little bit of power lost, but we're going to talk only about ideal transformers. But you can't just generate power out of nowhere. So something else that we know is that the power in the primary transformer or in the primary coil has to be equal to the power output in the secondary coil. And substituting some equations we've learned previously, the power is equal to the voltage times the current. So the voltage in the primary times the primary current is equal to the secondary voltage times the secondary current. And as we can see from this equation, if, for example, the primary current was 10, and the primary voltage, was 10, and the secondary voltage was, let's just say 100. Okay, and then let's say that the primary current is also 10. You can see that if we increase the voltage, in order for this equality to hold true, the current would have to drop. So the secondary current would have to be 1. So what this is showing us is that if we increase the voltage, the current goes down. And this is how we use these transformers and apply these principles to the transportation of electricity across countries. Let's take a look at an example. So a step-down transformer has 7,500 turns on its primary coil and 125 turns on its secondary. The voltage across the primary is 7,200 volts. Find the voltage across the secondary, and the current in the secondary is 36. What is the current that flows through the primary? So for part A, writing down what we know, we have that the primary voltage is the primary coil turns is 7,500 turns. And in the secondary, we have 125 turns. The voltage in the primary is 7,200 volts. And the voltage in the secondary is unknown. So just using our equality, because we know that we looked at using our magnetic flux equation, we can set up our equality here, Vp over Np equal to Vs over Ns, and we're just filling in some numbers. 7,200 over the number of turns is 7,500 is equal to the secondary voltage over, where are we at, 125. And rearranging, we get a secondary voltage of 120 volts. Okay, and the next part of that question was looking for the current in the primary voltage, or the primary coil, sorry. So in this part, let's see what we have. We now know that the voltage in the primary was 7,200. The voltage in the secondary, we just learned, was 120. We were given the current in the secondary is equal to 36 amps, and we're asked to find the current in the primary. Okay, so for this one, we use our power, our fact that the power in the primary is equal to the power in the secondary coil. So Vp times Ip is equal to Vs, secondary voltage, times the secondary current. Filling in our numbers here, so 7,200 volts times our primary current is equal to 120 volts times 36 amps. And we get a primary current, so that input current was 0.60 amps.